his master's thesis today. So I'll turn it over to Jeffrey, and then we'll do a time for questions at the end.
Thank you, Dr. Flowers. All right, so I will share my screen. Let me do that. Just make sure sound is on. So, yeah, that's fine. I guess it doesn't matter. My lighting doesn't matter.
We can still see you.
Yeah, as long as you can see me, that's fine. Okay. Let me get started. Everybody can see my shared screen, right? Everybody can hear me okay? Okay, thank you. All right, so my project is called Partition Properties from the m-ary tree observations. And my advisor is Dr. Flowers, and we looked at some extensions of the Calkin-Wilf tree. So let's get into some of the overview of what this presentation will be about. So we will start by giving you a little bit of background information. We'll talk about some background math that we'll need for this presentation. So we're going to look at some generating functions, some integer partitions, and we're going to be looking at some different types of sequences, such as the hyperbinary sequence. And then that'll lead us into some of the different tree levels, such as the Calkin-Wilf tree, the m-ary tree. And then we'll try to make some generalizations about the m-ary tree, and we'll conclude. So let's get into it. So let's talk about what this topic actually is. So the famous question everybody says is, what's your thesis about? And it's always hard to explain without going into like oh, you need to know about this and this and this. So let's just give with brief background information about the Calkin-Wilf tree. So around the year 2000, there's some authors, Neil Calkin, and I think his name was Herb Wolf. They found an alternate method of counting the rational numbers. So there are different ways that we can count the rational numbers, but when we get to the Calkin-Wilf tree, I'll mention some of those other different methods that we can use there. But some of this paper that we'll talk about is, so we'll need to know how they found this, and we're going to look at some different types of partitions and generating functions that'll lead us into different sequences, so that way we can see how they did this, and then we can extend it even further. So one of the most common forms that they used was they used the hyperbinary sequence, and they found ratios of different sequences for that to see how they can form the sequence of rational numbers. So I will, in this paper, talk about the m-ary tree and make comments on the 5, 6, and 7, and then talk about the m-ary tree. But I will examine the Calkin-Wilf tree and the m-ary tree that has been previously researched. All right, so let's get into our first definition. So our first definition is an integer partition. So if you have taken a number theory class or a combinatorics class, you would know that an integer partition is defined as finding the an unordered sum of parts less than or equal to n. Right, so the order usually doesn't really matter, but we do usually list it as a non-increasing order. So let's look at an example of what an integer partition actually looks like. So an integer partition, we can have, for example, integers 1 to 5, and we could see 1 would be as parts less than or equal to n, or 2 would be as just 2 or 1 plus 1, or 3 would be 3 as 2 plus 1 and 1 plus 1 plus 1. All right, so what we can do is have equation 1 down there, and we can often express a partition as the number of parts that are listed. And at the bottom of the screen, I kind of have an example of how kind of that looks. So take integer 5 for my example here. There's a good number of ways at the top there. We can see how we can list 5 as an integer partition. So we can just have 5 to the first, just one 5 part. Or if we look at the second to last, there's 2 plus 1 plus 1 plus 1. So that'd be the second to last one down there at the bottom of the screen. We have 2 to the first, and then we have 3 parts of 1. So this is just a common way that we can express integers as a partition. So this allows us to go into finding the number of unique integer partitions for n. And we usually denote that as the classic P of n. And it's defined for where the partitions of 0 is always 1. So we can then define the sequence for this as P of 0, P of 1, where we can find how many partitions there are for that integer. And I have that listed in the middle equation there, where we can see that there's 1 way for 0, 1 way for 1, 2 ways for 2, 3 ways for the, etc. And then this leads us to the following equation at the bottom of the screen, where we can see how we can find integer n based on the number of parts that we have. And if you take a number theory or one of these classes, this is a common representation. If you wanted to see more examples, I have a paper referenced here that you can always say, email me your paper, and you can look at more background information of integer partitions. But there's one more thing I want to talk about with integer partitions, and that's a Ferris diagram. So a Ferris diagram is another classic way to visually represent partitions. So for example, here on the page, I have integer 10. So integer 10 can be represented as 4 plus 2 plus 2 plus 1 plus 1. And if we represent it as a Ferris diagram, we can list this as an array of dots. And we can see we have 4 dots in the first row, and then we have 2 dots, 1, and 1. Again, this is another common representation for how we represent integer partitions. Depending on the size of the integer and the partitions, they can get very large. So there are alternate methods of representing integer partitions, but this is a classic common introduction way to represent them. Okay. So let's actually talk about some generating functions. So now that we know a little bit of integer partitions, we can actually start leading into functions. So what is an integer? What is a generating function? A generating function is used to represent series or different sequences, and we can use these as counting problems. So if you've taken Math 643, the Combinatorics class, this is a useful tactic in our counting problems. So let's say I have a coefficients down below. We have H0, H1, H2. And we can generate this as a sequence, an infinite sequence. And I have that listed as equation 3 there, where we can have some coefficients H0 plus H1 times its corresponding term. And we can use this now to have, so we can use this when we're trying to represent finite and infinite sequences. So let's say I had a finite sequence. I can represent that as an infinite sequence where the rest of the terms would just be 0. And it would still give us a polynomial, which I have listed there as g of x. So this represents us to the official definition of what a power series is. And I have that listed as definition 2.2 on the screen here. So if we have some coefficients, we can denote them as A0, A1, A2. We can represent this as a power expansion. And if you've taken a calculus class, this is something you might have seen before. It's common. So why do we need these? Well, let's see if we can try to start building some generating functions. And I want to look at a specific generating function for a coefficient of 1. So if we have 1, 1, 1, 1, it keeps going. How would this look as a generating function? Well, on line 2 there, I have g of x represented as 1 plus x squared, and it keeps going, where think of those h terms as 1. And if we try to create the generating function for this, we could have it as equation number 4 as 1 over 1 minus x. Now, I'll reference this later in the paper still more often, but for right now, this is one of the basic common forms of a generating function. There are many different types of generating functions, such as ordinary generating functions, exponential ones, Lambert, and I think if I pronounce that right, Dirichlet. We might have seen that, I think, in Dr. Crispell's class last semester. I think he introduced us to this, but there are many different types of generating functions. We'll be looking at some basic ones that we can use to represent for our binary sequences. Okay, so let's look at one more example. Let's consider a product of the generating function 1 plus x to the I power. Well, if we expanded this, we get the following equation on the first line, right? But what happens if we expanded that further? Well, then we get the equation on line 2 there, and it's 1 plus x squared plus 2 to the x to the third, etc. But what I really want to look at is an example of this and why this is important. So let's look at that term 4x to the 6. What does that 4x to the 6? So what's that 4 mean on the x to the 6 term? So this is really why generating functions are very useful in counting problems, is because it can tell us the number of ways to find that part. So in this case, if we can see that there's 4 ways to generate that x to the 6th term. And I have them listed on the screen here. We have that x squared, that x to the 4th term. We have x to the 1st, x squared, x to the 3rd, or just the x to the 6th term, or that just single part of x to the 1st and x to the 5th. And that tells us there's 4 ways to construct that. So these generating functions are very useful, and we can relate these to our partitions so we can find the number of partitions that we want. So let's try to see if we can do that. So first I want to prove a theorem, which will lead me into the part that I want to see so we can use a generating function from this to help us do our counting problems. So let's start with theorem 2.1. If we can prove this, with generating functions. So the theorem says, hey, if we have the number of partitions of some integer n where each part occurs at most 2 times, this is claimed to be equal to the number of partitions of n where they are not divisible by 3. So as I said, we could do this by finding the generating function for each and see if they're the same. Okay, so let's start by finding the generating function for parts not divisible by 3. Well, looking at this generating function, we can see that if we remember that 1 over x minus x, we can expand this by finding parts. So we can find this by expanding parts of 1, parts of 2, and excluding the parts of 3. So I'll show this more on the next page, but this is parts that are, the exponent tells us the number of parts that are included. So if we factor this and create a generating function out of this, we can create the generating function on line 5. And we can see that to be expanded, that is true. So if we look at the parts for the partitions of where parts occur at most 2 times, I want something that looks like what's on the first line. So if we have 1 plus x squared, picture that 1 as x to the 0 where there's no parts of 1. And then that x to the 1st is parts where there's 1 part of 1. And that x squared is 1 plus 1 where there's 2 parts of 1 occurring at most 2 times. And then that x squared would be 1 part of 2 x to the fourth could be 2 plus 2 as 2 parts of 2. And then the same would be the x to the 6th, which is 3 plus 3 or 2 parts of 3. So if we wanted to form this, we can find the generating functions by making these ratios of these generating functions, which is 1 minus x to the third over 1 minus x, and we can continue them as they go. And if we tried to simplify this, we could see some certain things will cancel out, and we get the following generating function on the third line, which reduces down to equation 6. And we could see this is going to be the same generating function as the parts not divisible by 3. So the theorem is true. Okay.
Jeff, can you show me the previous page for just a second?
The previous page?
Yeah.
Yes.
Okay, thanks.
No problem. Okay, so now that we understand integer partitions and we know about generating functions, let's lead into some of the levels of sequences and see if we can make some generating functions for these. So first, let's talk about the most common one, the hyperbinary sequence. So what is the hyperbinary sequence? The hyperbinary sequence tells us that if we want to create some integer n as represented as the sum of powers of 2, where each power is only allowed to occur at most 2 times. And we denote this by h2 of n. So I have an example on the screen there. Let's say I have integer 11 and I wanted to find all of the hyperbinary representations of integer 11. To do this, we can see we have 2 squared, plus 1, plus 2 to the 0 power. And then the other way would be 2 to the third plus 2 squared plus 2 to the 0 power. We can see that there are only 2 ways to represent 11 using powers of 2, where each power occurs at most 2 times. So I define the following as h2 of 11 is equal to 2. Okay, so binary partitions have been around for a long time. There are other authors like Euler, our good friend Leonard Euler. He actually studied some of these, and Arthur Churchhouse actually continued some of his work, and there's a paper on it where he defined the following theorem. Well, definition. So he defined the binary partition function. So the binary partition function is denoted as b of n, where we denote the number of ways of expressing some positive integer n as a sum of powers of 2, but in this case, the powers are not limited. It is defined for where b of 0 is 1. Okay, so there's one way to get 0. And as I mentioned, Euler, he studied some of these. I read a little bit of his paper, but not a full paper on the background information. But one of his colleagues and them were just trying to define more recursive formulas to get different partitions for powers of 2. And as I said in the example before, there's powers of 2 are a very promising topic. We could see these, I guess, outside of accounting problems. We can look at the set theory. We can see the power set will have 2 to the n members. So there are many different applications for powers of 2. For this paper, I'm not going to go into all the different areas of what powers of 2 are useful for, since there are a lot. But this is where they kind of stem from. So let's look at some different cases of hyperbinary sequences. So the hyperbinary sequence, we can represent this recursively. But to do this, we need to consider some different areas of hyperbinary sequences. And then by that, I mean we need to consider even and odd partitions, because we know even and odd numbers can make up composite numbers. So let's just start by saying, let's look at an odd number. And as math people, we should know that an odd number is in the form of 2m plus 1. So this isn't a formal proof to the theorem I'm leading up to, but these are the ideas of what I'm trying to show. So if I have a number that's odd, what I can say is, hey, if I look at that plus 1, that means there's a 2 to the 0 term in there. So if it's in there, it'll either occur an odd number of times or just exactly once or an odd number of times. So if we remove it, divide by 2, we can get the partitions of n. And if we go backwards, starting with the partitions of n, multiply by 2, add in that term of 1, we can see we also get a 2 to the n plus 1 expansion. So this implies in equation 7 that the hyperbinary partitions of an odd number are going to be the same as the hyperbinary partitions of some integer n. So if I illustrate this truth in example, recall that I had integer partitions, or the hyperbinary partitions of integer 11 before. We found that there are 2 ways. So by the theorem, 2 times 5 plus 1, 5 should be the same as the hyperbinary partitions of 11. So I listed them on the screen, 2 to the 0, to the second, to the 0, to the first, where each power occurs at most 2 times. We see there are only 2 ways to represent integer 5 as powers of 2, occurring at most twice. And it's the same as the hyperbinary partitions of 11. We can make the same argument for even numbers too. So if we have 2 to the n plus 2, we can follow the same type of logic. We can get rid of the 2 term, divide by 2, get n, or we can also just have no parts of those 2 to the 0 powers, divide by 2, we're left with n plus 1 expansions. And then we can find that we'll get the following theorem, we'll define on the next page, but we can see we find this nice pattern where the hyperbinary partitions of 4 will be the same as the hyperbinary partitions of 2 plus the hyperbinary partitions of 1, in my example of when n equals 1. So if I show when n is equal to 1, we'll see that we'll get the hyperbinary partitions of 4. I find 3 ways to do that. if I find the hyperbinary partitions for 2, there's 2 ways to do that. And then we already defined that the hyperbinary partitions of 1, there's going to be only 1 way to do that. So 2 plus 1 is 3. It's going to be the same. And then this is where we can define it as an official theorem. So this is called Stern's diatomic sequence. So Stern's diatomic sequence is defined as binary partitions. So we start at the hyperbinary partitions of 0 is equal to 0. And we have the following that we just kind of explain the logics of the proof for. So Stern's diatomic sequence isn't exactly equal to the hyperbinary sequence. So note that when I had B of n, so B of n is actually equal to Stern's diatomic sequence for n plus 1. So it's just shifted plus 1, and they just have an extra 0 term at the end. But we can keep this similar notation. So we follow with the same notation and logic throughout the paper. So if you did want to see the official proof of the ideas that I referenced in the last 2 slides, you can read the Dickler and Erickson paper where I read these from. But we will refer to these ideas for a later proof when we look at the 3-ary tree. Okay. So we can actually have if I can pronounce that word, corollary from the previous theorem. So we can see that if we have an integer in the form of 2 to the k minus 1, all of these partitions will be 1. And we can prove this true using induction. So induction is a pretty straightforward method of an undergraduate proofwriting method. So just to walk you through it really quickly, it'll work for the base case when n is 1. Well, when n is when n is 1, so it'll work for that. We can assume it's true for the hypothesis step. And then if we go through and do the induction step, we can see that it'll also be true, and it'll work for every integer 2 to the k minus 1. Okay. So now that we're outside of that, we can start moving into the hyper m-ary sequence. Since we already talked about the hyperbinary sequence, there's other different levels of the m-ary sequence, and other than 2. So let's actually define what a hyper m-ary sequence is. So the hyper m-ary sequence is defined by saying we have some integer n where we can represent it as all parts of powers of m, but each power can occur at most m times. We denote this as h of m of n. So for example, when I said the hyperbinary sequence, that's h2, powers of 2 occur at most 2 times. If I said hyper 3-ary, well, then that's powers of 3, each power occurs at most 3 times. M powers at most m times. So there's actually a really cool paper from Courtwright and Sellers called Arithmetic Properties of Hyper m-ary Partition Functions, and they actually proved a really cool theorem. So we get to theorem 3.1 here, where they say if we have a hyper m-ary partition of some integer n, the following 2 equations will hold. So we can find these recursions for finding the product of the hyper m-ary partitions of m times n, and we can see that these 2 will hold. So it's really cool that equation 12 is valid, and we will show this truth in an example in a moment, but we can see that it's going to give us a range of R for where R is bounded between 1 and m minus 1. And of course, we have the initial condition again, so no matter what tree or at least the sequence you're looking at, so it'll always be, so hm of 0 is always going to be 1. So let's actually show this true with kind of an example. So let's just say I chose n equal to 10, and we're looking at the hyper 5-ary sequence, where each power can occur at most 5 times. Then equation 11 will claim that the hyper m-ary partition, or the hyper 5-ary partitions of 50 will be the same as the hyper 5-ary partitions of 10 plus the hyper 5-ary partitions of 9. So I actually wrote so part of my thesis was writing the code. So I wrote a code for the hyper 5 m-ary, or for the hyper m-ary sequence for any integer n. It almost worked once you get the high values, as depending on what m is and what n is. I might be missing 1 or 2 partitions, but I was able to go through and I was able to type in, my function of 5, 50, and it was able to give me the partitions, which was very convenient. So if we look at the hyper 5-ary partitions of 50, we get 3 ways to do that. So I won't read through them, you can see them on the screen, where each power occurs at most 5 times. So if I find the hyper 5-ary partitions of 10, there are 2 ways to do that. They are listed on the screen. We get 5 to the 0 power 5 times. And we find the 5-ary partitions of 9. There's only 1 way to do that. And we can see that theorem will be true. So 2 plus 1 is 3, and it's true. So you can actually verify these online. There's called the OEIS. That's called the Online Encyclopedia of Integer Sequences. And there's so many sequences online that there's a whole list of them on there. So you can find the hyper 5-ary, the hyper 4-ary, the hyper binary. You can find them all on there, and you can verify these. So it was nice when I was writing my code. This verified it for when I was building my code, and I realized, oh, I'm missing one, but you can still verify these online. So the theorem is true. Okay, so I want to prove that equation 12. And if you don't remember that equation 12 is, that's okay. It was that hyper m-ary partitions of the product of m times n plus that R value, where I told you R was bounded between 1 and m minus 1. So if we stick with our example of H5, that means R is going to be bounded between 1 and 4. And all that theorem is telling us is if we get to plus 1 value each time from where R is between 1 and 4, that's telling us the hyper 5-area partitions of 51 and 52 and 53 and 54 will all be the same. And we can actually go ahead and do this. So typing in my thesis code, I tried to find my hyper 5-area partitions of 51. It went ahead and did that. And we can find the 2 ways to do it here. But then look at 52. All we're doing is tacking on a 5 to the 0 power. And if we do 53, we're just tacking on another 5 to the 0 power. 54, another 5 to the 0 power. So you're probably thinking, why isn't 55 also the same? Well, once you get to 55, you can make more powers of 5 that will occur another way. And it's actually 3 ways to do it. I don't remember what the partition is off the top of my head, but there's another way to do it, which gives you a total of 3 ways. But that is a very unique theorem that Corrate and Sellers actually proved. And I didn't prove it in here, but you can, I referenced it in their paper. So you can see their paper if you wanted to see the full proof for that. But we can verify these these partitions based on the online encyclopedia of integer sequences. Okay. So one more thing that I want to talk about in these sequences is let's actually now define a generating function for the hyper binary sequence. So recall when I said that equation 4 before. If you don't remember equation 4, that's okay. It was just a generating function of 1 over 1 minus x. So if I take that generating function, and let's say I replace x with x squared, then I get the parts of 2 like I mentioned before. So I get 1 plus x squared plus x to the 4th, etc. If I replace it with a 3, well, x to the 3rd, it'll give me the parts of 3. So we can finally deduce the generating function from partitions. And we get the following generating function on the bottom of the screen where we get the product of 1 over 1 minus x to the jth power. So we can get the parts of what we want for partitions. So this will then lead us into saying, okay, so if we have the partitions that we want, how can we limit it so we can start forming these hyper-ary sequences so that way we can limit to the number of parts that we want. So in this case, if I go back, I can say, so remember when we proved the parts occurring at most 2 times, we can recall this form. We can say we have 1 over x to the 3rd divided by 1 minus x. This will give me the generating function for parts that occur at most 2 times, where in this case, it's part of 1 occurring at most 2 times. The second one I have in the middle of the screen is going to be parts of 2 occurring at most 2 times. And then the same as parts of 4. And you can keep it going for whatever parts that you want. You just have to be careful on the multiples. So then this leads us saying we can find this is the generating function for powers of 2. So in this case, we just have it as 1 minus x to 2 raised to the jth power, because then this will now give us powers of 2. So then we can finally define the following theorem in definition 3.3. So we can define that the hyperbinary partitions of n will be listed as the following generating function, where we have the following generating function where it's 1 over x to the 3 times 2 to the jth power divided by 1 minus x to the 2 to the jth power. And this will give us, like we saw on the last page, where we can limit the number of parts to give us just powers of 2, but occurring at most 2 times. So this is really unique because we can find this for any generating function, for any power, for any m. Only you would just have to change the coefficients of 3 times 2 and 2. So that way you can make sure that if you're doing 4 or 5, the powers occur at most a certain number of times. So let me check the chat real quick. There is okay, that's okay. I thought there was a comment or a question. So this is nice because we can find the generating function for the hyperbinary sequence. So I left it as an exercise if you really wanted to go. I could show for whatever, generating function for different H4, H5, it's just, you just have to change the number. So I left this as if you wanted to go off and find your own, you can. Okay, did not let me click. Okay, I guess let me click now. Sorry. So now that we have all that background information, let's start diving into the tree levels. So we can go back and start with the Calkin-Wilf tree, and that's the most basic level of the tree. So this is when m is equal to 2. So this is the 2-ary tree essentially. So this originally wasn't called the Calkin-Wilf tree. So Calkin-Wilf actually went back and they actually referenced some old papers. They actually referenced some old work, which some of it was by author Stern, which is where we saw Stern's diatomic sequence. So they realized that there was another way to count the rational numbers other than using Cantor's theorem. So you might have seen Cantor's theorem in an undergraduate math class where they use the power. The theorem is defined as looking at the power set. And all that theorem is saying is just by saying, look, the power set of some set A. So I have an example of 1, 2 will be strictly less than the power set, which is where it's just all the subsets of that set. So I have the empty set 1, 2, and 1 and 2. So if using that theorem, you can go off and you can prove the cardinality of the rational numbers by making a 1-to-1 correspondence. I won't show that in here because that's not super relevant, but it is another alternate method of counting the rational numbers. So they didn't come up with this idea fully. There was, like I said, author Stern, he kind of had some of these ideas and they just kind of put them together and they said, hey, this is true. And then eventually it got named after them. So how do they do this? So looking at the hyperbinary partitions of n, they found if they take ratios of the number of hyperbinary partitions of n divided by the number of hyperbinary partitions of n plus 1, we find that we can get every rational number to occur. So we have the following definition called the Calkin-Wilf tree. So the Calkin-Wilf tree, instead of listing it, you can list it as a sequence, which I will show on the next 2 slides, but they label these as a representation as a tree. So they label this as starting with parent 1/1 because that's the most basic form of a positive rational number. And then they have 2 children defined as a over a plus b and a right child a plus b over b. So if we were to look at the tree, it is the following here. So it starts with root 1/1, and they have left child a over a plus b. So in this case, it's 1/1 plus 1. Second child, 1 plus 1/1. And then this just keeps going. So we know that there's endless rational numbers. So it's going to keep going. This will expand even larger. But these are just the first 4 levels. You can see that when you get to 1/2, you get the following definition to occur again, 1/1 plus 2. And then the other definition would be 1 plus 2 over 2. So it keeps going. So we can list this still as a sequence. So we start from left to right from each row, and we write them from left to right, and we can get the following sequence. We know that each vertex has degree 2 because it's a binary tree. And if I were to just say randomly looking at the 8th term in the sequence, it's going to be 1/4. Okay. So just to recap one more item, we know that the next term, they found that the next term in the sequence is by this ratio of hyperbinary partitions. So we know that this will work for n being greater than or equal to 0, where the root is always 1/1. And there's actually another paper by Bates and Mansour. They expanded on this a little bit further. They saw that, hey, well, if you don't want to calculate the hyperbinary partitions of some integer, we can make a recurrence for this. And they say, well, if we know what the first term is, so we can start with C1 defined as 1/1, you can have the following recurrence at the bottom of the page there. So you can just make a sequence, you can write code and it would just go through and generate all the integer sequences for you. And it's just an alternate method of if you wanted to calculate the next term in the sequence. But if you wanted to see the proof for that, I can reference you that paper. Okay. Was there a comment? No, okay, I was just making sure. Oops, didn't mean to skip. So this leads us into the following, this picture, just me, I bumped the click button. So just let's lead into the following few lemmas that they proved using their idea. So they claim that every numerator and denominator are relatively prime at each vertex on each level. So how do they prove this? Well, they prove this by contradiction. And to prove this by contradiction, they say, let's start with some fraction u over v, where it's on the tree. And what they do is they say, well, this fraction must stem from some parent. And since it stems from some parent, depending if it's a left child or a right child, that means the numerator will be bigger than the denominator, or the denominator will be bigger than the numerator. So if it was a left child, for example, they say the parent will then be u over v minus u. And since it's not a reduced fraction, they say it's a contradiction, and every fraction must be relatively prime. And they make the same argument for when it's a right child. It's just, the numerator is bigger than the denominator, but it is proven to be true. So let's look at the second lemma, or the second idea that they proved. So they say all reduced non-negative rational numbers will occur at some point. And this is kind of a big idea, but it's not official until we get to the next slide. But they're claiming every rational number will occur. So they start with the number 1/1, which is the root. And we know that it will occur because it is the root. And it's not going to repeat itself because based on the definition of the tree, the numbers stem from each other and they keep getting larger. And then they look at some fraction u over v, where we can have 2 different cases where, the numerator is bigger than the denominator is bigger than the numerator. And what they do is they try to minimize it, and they look at the parent, saying the parent is not minimized, therefore the fraction cannot be minimized. And they show that it is true. So some of these arguments that they do, they use similar logic for, and there's a little bit of overlap. But it does prove that every rational number will occur at every vertex because of this minimization of the fraction that's stemmed downward. So the last idea, which is kind of the big point of the Calkin-Wilf tree, is they say, okay, well, every rational number will occur, but it will only occur once. And that's kind of the big thing, is there's no duplicates in this tree. So 1/1 will occur at the root. It's the same idea as before, that they stem further and 1/1 will not repeat itself. But then if we say, well, let's choose some fraction u, we're going to prove this by contradiction again. We'll look at the definition of the tree, and we'll look at two different cases. So I just wrote the case for when, I think it was the denominator is bigger than the numerator. It'll be the same case for when the numerator is bigger than the denominator. What they do is they say, let's look at some fraction. We'll look at its parent. And if it's a left child or a right child, if we find its parent where it's non-reduced as well, then something, this can't happen because it won't be the same as what they're saying won't happen because they stem from the definition of getting larger and they'll all be unique. So this is a really unique property of the Calkin-Wilf tree that every rational number just occurs once. And we're going to use this idea when we prove a bunch of other stuff later. So now that we talked about the Calkin-Wilf tree, which is the level 2 of the tree, let's actually get into the 3-ary tree. So the 3-ary tree is an extension of the Calkin-Wilf tree, and it's defined by the following. So the Calkin-Wilf 3-ary tree is defined by having still root 1/1, but this time we have 3 children instead of 2 children. So some fraction a over b will have children a over a over a plus b, and a plus b over b. Okay, so let's take a look at what this tree actually looks like. So the tree is quite big. So you can see it stems to root 1/1. And the first child will be a over a, which in this case is just 1/1. So try to remember that, or at least take note of that. And then the second 2 children are noticed to be the Calkin-Wilf children. So now we can still look at the sequence one more time. We would still read it in the same order as from left to right, where we go from each row left to right, and there'll be the next fractions in the sequence depending on the next row, left to right, next fraction in the sequence left to right. So let's actually compare the 3-ary tree and the Calkin-Wilf tree. So what's unique about these two? So we can notice that the Calkin-Wilf tree is embedded within the 3-ary tree. And we know that to be true because in the definition, the Calkin-Wilf children are the second and third children. So this tells us that the Calkin-Wilf tree is a subtree of the 3-ary tree, but not every element of the, or at least fraction of the 3-ary tree will be within the Calkin-Wilf tree because it's larger. We can also denote one more item that even though that the Calkin-Wilf tree is within inside the 3-ary tree, since that first child by the definition is a over a and it stems from root 1/1, then that's telling us that every fraction will repeat itself an infinitely number of times, right? So if I go back to the picture, we can notice that 1/1 is repeating itself a multitude number of times. So you might be able to see my mouse if I move it. 1/1 will repeat itself an infinite number of times, which will stem Calkin-Wilf trees, which means every rational number will occur an infinitely number of times. Okay, so let's actually look at some things that were proven about the 3-ary tree. So I have the following lemma here. Given a denominator of some fraction a over b, it's claimed that the next fraction in the sequence will have numerator of that denominator. So if some fraction is a over b, the next fraction in the sequence will have numerator b. So how do we prove this true? We could prove this true with induction. So there's actually a paper on this that proves it true. So I won't read it verbatim, but I'll explain the idea of how the proof is done. So we know if we prove this by induction, we know that it'll work for the base case. We'll assume it up to the kth level, and then we'll look at the induction level of k plus first level. So the way they prove this true is they start by considering both cases, whether it's a left child or a right child. And if it was, say, for example, a right child, well, then by the definition of the tree, a plus b over b, then the parent must have the same denominator as the last child. And then if we go through and push the induction step through, we'll see that it will have the same numerator as the next following fraction. And if we do that too with the leftmost child, if we push the induction step through, it'll also have the same numerator as the next following fraction. This is just, the proof is quite long. It's, if you wanted to see the full details of it, there's a Flowers and Lockhart paper that did a lot of research on the 3-ary tree that I have referenced as my reference 9. So, but this explains the idea of how they prove it true with induction, and it is true. So let's actually look at one more thing about the 3-ary tree. We can actually define the nth term in the sequence by looking at the hyper 3-ary partitions. So it is claimed that the hyper 3-ary partitions of n-1 divided by the number of hyper 3-ary partitions of n will return the nth fraction in the 3-ary tree. And we can also make a note at the bottom of the page there that we can also find the next children, because if we look at multiples of one another and subtract by 1 or 2 terms, we can get the next terms in the sequence. And we can actually prove these true. So we can deduce that 3 to the n, the hyper 3-ary partitions of 3n-2 are going to be the same as the hyper 3-ary partitions of n-1. And we'll say the same for the following. So hopefully you kind of identified that this is kind of similar to the logic that we did when we talked about Stern's diatomic sequence, and we can actually formulate these in a official proof here. So it's still defined that, as we call hm of 0 is always going to be 1 no matter what m you're dealing with. Okay, so let's actually prove the theorem true. So let's start by looking at the hyper three-area partitions of 3n plus 1. So we know that this will be congruent to 1 mod 3. And what we can do is use that same logic as before by doing algebra and rearranging. We can look at the hyper three-area partitions of n plus 1. So we know there's going to be a part of that 3 to the 0 in there. If we rearrange it, divide by 3, we can get the hyper three-area partitions of n. And if we start with n, we multiply by 3, add in that individual term, we can get the hyper three-area partitions of 3n plus 1. And this is explaining that the hyper three-area partitions of 3n plus 1 is going to be the same as the hyper three-area partitions of n. We could do this true with the 3n plus 2. And it's the same thing, only in this case, you have to see that it's equivalent to 2 mod 3. If we rearrange the terms again, we'll just have those two terms of 2 to the 0. But if we subtract them, divide by 3, you're left with an expansion of n. But then if you go the other way, we can multiply by 3, add in that 2. You're still getting the expansions of 3n plus 2. And this proves that the hyper three-area partitions of n plus 2 is going to be the same as the hyper area three partitions of n. The last step would be to looking at the hyper three-area partitions of 3n plus 3. Only this time we have two cases, whether there be 3 parts of those ones or there be none. If they were present, well, then we can rearrange them by subtracting them, divide by 3. We get the hyper area three partitions of n. And then let's assume there were no parts of there. Well, then we just divide by 3. We're left with the hyper three partitions of n plus 1. And then this explains the following equation at the bottom of the screen. It proves it true, showing the hyper three partitions of 3n plus 3 are going to be the same as the hyper three partitions of n plus the hyper three partitions of n plus 1. So we can prove that proves the theorem true. Okay. So now we can get into what I started to research, was the 4-area tree. So we talked about the Calkin-Wilf tree, we talked about the 3-area tree, but let's start looking at some other unique trees, such as the 4-area tree, and see if we can look at maybe some other comments of 5, maybe some 6, and see if we can make some generalizations. So let's just start with the 4-area tree. How is the 4-area tree defined? Well, the 4-area tree is defined by having root 1 over 1, where we still have this time 2 children. So some fraction A over B will have 2 children in front as A over A, and then the last 2 children are A over A plus B and A plus B over B. So we can easily see that the 3-area tree is an extension, or the 4-area tree is an extension of the 3-area tree. So if we were to look at the expansion of this, it does get quite large. It's a lot of fun to type in tech. We can see that we'll start with the root 1 over 1 again. We'll have 2 children of that A over A, and then we have the last 2 as the A over A plus B and A plus B over B. And they do get quite large very quickly. And we can still define the following sequence again to be from left to right from each row that we start on, and we can find the terms in the sequence. Okay. So let's talk about some observations that I found. And this is based on the 4-area tree to start. So I found something really unique. So as I said before, I coded in Python the hyper m-ary sequences for some integer n, and it almost worked except for large values. But I was able to code up the 3-area tree, the 4-area tree, the 5-area tree, and the 6-area tree, and the 7 at the end. But starting with the 4-area tree, I had a bunch of for loops, went through, tried to see what other patterns I could find, and I found something really unique, and I really like this. So let's assume we have some fraction A over B. If the parts A over B are relatively prime, so then the first time it'll occur will be the first time, the second time it'll occur will be twice, and then after that, it will be 3 times the previous row. And it follows the sequence on the screen. So 2, 3, 6, 18, 54, and it keeps going. So I used a little bit of Mathematica to help me generate a closed form for this, and it can. And Mathematica returned for me that the fraction A over B will occur on some row R, where it'll occur 2 times 3 to the R minus 1 times on that row after W, where I define W being the row it comes for the first time, where it will appear exactly once. So we can go ahead and prove these in a series of lemmas. So let's start with this lemma, lemma 8. So we first need to define and just make it noteworthy that it has to, at least that we're aware of it, that every rational number will occur an infinitely many number of times. And we know this to be true because when we looked at the 3-area tree, we know that the Calkin-Wilf tree is embedded within the 4-area tree and the 3-area tree. And since the definition states will have those repeats of the Calkin-Wilf tree, every number will occur an infinitely number of times. So it's still worth mentioning that. So let's actually go ahead and start proving this. So the first lemma I want to talk about is saying, hey, given some fraction, let's just call it x over y, the first time that it will occur will be exactly once. So how do I prove this? Well, let's start with some fraction x over y and look at its definition of its children. Its children will be x over x, x over x, x over x plus y, and x plus y over y. So if we look at the last 2 children, they're the Calkin-Wilf children. The Calkin-Wilf tree is embedded in the 4-area tree. And we know by definition of the Calkin-Wilf tree that every rational number will occur once. So the first time that that number will occur must be 1 time. And that is proven to be true here, that every rational number, that time that some fraction we'll call it x over y will occur will be the first time, and it will be occurring exactly once. So let's go to lemma 10. So if I claim it, So lemma 9 claims that it'll occur for the first time once. Now we say if some fraction x over y appears for the first time, we'll call it on some row. We'll call it r for the lemma. Then the next time it occurs, which will be on row r plus 1, will be exactly 2 times. And I prove it by looking at the definition again. So we see we have the 4 children defined as x over x twice, x over x plus y, and x plus y over y. So if we look at those first 2 children are going to be copies of the Calkin-Wilf tree with factor x, which will allow the replication of that fraction x over y. So that means on the next following row, row r plus 1, it must occur a total of 2 times. And this is proven to be true. So then my last lemma that I want to look at, and I have an example here to illustrate it. So if I have some fraction x over y, and after the first 2 times it occurs, well, so after when it occurs on some row later than the first time and the second time, then on some row, we'll say it'll occur exactly L times. And then what we want to say is on the row after that, it's going to occur 3 times the previous row. So let's look at the following figure I have on the screen. So the first time I chose some random fraction 2 over 1, it's going to occur for the first time as 1 time. The second time it'll occur, we prove that it's going to occur exactly 2 times. And then let's call this just row L, even though it's right at the beginning, it's row L. The next time it'll occur 3 times the previous row. So it should occur 6 times down here. And it does 1, 2, 3, 4, 5, 6. So this just kind of illustrates the idea of what I'm trying to prove. So how do we go ahead and prove this? Well, I'm going to look at the definition of the tree again. And I already proved it occurs once for the first time, twice on the row right after it occurs for the first time. But then now, here's where the cool logic comes into play. If I look at the definition of the tree, it's x over x, x over x over x plus y, and x plus y over y. We already know that the first 2 children, the x over x's, will replicate a copy of that original fraction x over y. But then if we look at that third fraction by definition will allow more copies of that x over x, allowing replication of x over y, which will then in turn repeat another copy of x over y. So this tells us that out of all 3 children from the 4 in each time a parent produces children, that means 3 out of 4 children will be able to produce that fraction. And that means 3 times the previous row is proven for 3 out copies of that fraction x plus y on the next following row. And this is true. And that's how we prove it. So this allows me to lead into the following theorem. So if I have some fraction a over b in the 4-ary tree where a and b are relatively prime, so if it occurs once for the first time on some row we'll call w, then it will occur 3L times on some row r, where it will occur on a number of times of 2 times 3 to the r minus 1 on row r plus w, where we know the initial occurrence is 1 on that row w. So how can we prove this true? Well, the lemmas give us the ideas of the full details already. They kind of prove the ideas for us. That lemma 9 proved it occurs for the first time once. Lemma 10 occurs for this, the second time it occurs will be twice. And then after that, the lemma 11 will prove that after the second occurrence, it'll occur 3 times the previous row. And then we know the recurrence. If we go through and we look at a base case and we see it's a multiple of 3, it'll also follow that it follows this 3 times the previous row pattern. And it is proven to be true. Okay, so now that we talked about the 4-ary tree, let's dive a little bit into the m-ary tree and see what other things that we can talk about there. So if we know we made a definition for the hyper m-ary sequence, but now let's talk about the hyper m-ary tree, well, the m-ary tree. So the m-ary tree is defined as having root 1 over 1 with children from fraction a over b, having child a over a occur m minus 2 times, right? Because if this is an m tree, that means there must be m children, and m minus 2 children will be a over a. And that means the last 2 children will be a over a plus b and a plus b over b. So this follows the same pattern as the 3 and the 4, etc. So what can we see from this? So notice equation 13 should be familiar from when we found the nth term in the series, or the sequence from when we did the 3-ary tree, right? Because the Calkin-Wilf tree is unique, but then once we get to the 3-ary tree, a over a occurs once. 4-ary tree, a over a occurs twice. We can see eventually it's just going to occur in a number of times of m minus 2 times when we get to the nth level. And then we can see that the nth term in the sequence will be just the same ratio. So the hyper m-ary sequence of the number of hyper m-ary partitions of m minus 1 over the hyper m-ary partitions of n will be the sequence for how we can define the nth term for any level m. And what's really cool is we can also find the m children for this too. So depending on what m we're in, we can see I will go up from 1 to up to the nth, whatever m is, and we can find the m number of children for that nth term in the sequence, which is a really unique thing to do. Okay. So one more thing I still want to re-comment on, this is kind of a recap. We know we mentioned that the hyper m-ary sequence before from the core rate and Sellers recurrence, but we can see that this will still hold for any value of m. And if you did want to solve for it, you could still find what the hyper m-ary partitions of n are and the hyper m-ary partitions of n-1 are. Of course, you would still have to calculate the other side by hand, because if you try to write a code for this, obviously they get too large very quickly, and you wouldn't be able to do this recursively the other way around if you solve for the hyper m-ary partitions of n. But it's still worthy of noting that these will hold for any level of m. Okay, so let's talk about some parent generating functions. So as Calkin-Wilf have mentioned, when they proved their original paper, they did say that, hey, we have some ideas on how to generate a parent. So it is still worthy of mentioning that given some random fraction m, or some fraction a over b in the m-ary tree, we can find the parent of that fraction a over b given the following function. So if we have two cases, if the numerator is less than the denominator or the denominator is bigger than the numerator, we can see what the children are. And as long as a is not equal to b, we can still find the parent for that specific fraction. Unfortunately, this will not work for when a is equal to b, because if you could have some fraction 2 over 17 and the children will be 2 over 2, 2 over 2, and it's not easy to, it's not really possible to find that there. But it's still worthy of mentioning that we can do this for any size m. And we can prove this true by just choosing some fraction p over q and putting it through. We can see when a is not equal to b, we can plug in those values and we return the parent that originally it came from. And this proves it to be true. So there's another theorem I want to lead into, but since we're still talking about the m-ary tree now, it's still worthy of mentioning that every rational number occurs an infinitely number of times. Hopefully you probably saw this logic, but it's still worthy of defining it. The Calkin-Wilf tree lies within the m-ary tree. We know it'll occur once and it'll repeat the a over a or the Calkin-Wilf tree m-2 times. So we know that every rational number will occur an infinitely number of times, but we still worthy of mentioning it. Okay, so what now I want to talk about is another observation that I saw about the m-ary tree. So previously, like I said, I coded the 3-ary tree and the 4-ary tree to find some of the findings I did before. But now I was like, well, let me see what happens if I code up the 5-ary tree, the 6-ary tree, and the 7-ary tree. And there's some really cool computational evidence that I found, and I used Mathematica to help me out a little bit at the end there to see a closed form. But I found the following cool pattern. So at my last bullet point there, I say, notice in the 4-ary tree, remember I found my closed form that I defined as the following theorem and I proved true of 2 times 3 to the m-1. Okay, so if I coded up the 5-ary tree, I found that if if a fraction a over b where the parts are relatively prime, the same thing kind of occurs, but with a multiple, right? So it occurs in the form of 3 times 4 to the m-1. And then the 6-ary tree occurs in the form of 4 times 5 to the m-1. And then the 7-ary tree was 5 times 6 to the m-1. I was like, okay, I see a cool pattern here. And I was like, maybe I can prove this. So I formulate the following theorem. I say if I have some fraction a over b in the m-ary tree, and the first time it'll occur will be exactly once I call it on some row w. Then later, after row w on row w plus r, it must occur m-2 times m-1 to the r-1 times. And we can find this for any row r. So how do I prove this true? When I was looking at the 4-ary tree, I can use this same logic, this similar style logic to prove this true for any size m, because recall that the children a over a are just going to recur a multiple of, in this case, m-2 number of times. So I can start by saying, well, the first time that the fraction occurs will be 1 time. I look at the definition of the Calkin-Wilf tree. I know that the Calkin-Wilf tree is embedded in the m-ary tree. Therefore, by that, it must occur. Some fraction I call u over v must occur once on the initial row that it appears. So then I can go through and I can say, well, the second time it occurs will be m-2 times, right? Because if we look at the definition of the tree, some fraction u over v will have children u over u, a multiple of m-2 times. So if we see that it will replicate those Calkin-Wilf trees with factor u, my original fraction u over v will duplicate that number of times, meaning that it'll occur an m-2 number of times on the second row that it occurred, or the second, like the next following row it occurs. And then the last observation will be, well, okay, well, if it occurs exactly once the first time, m-2 times on the next following row, then after that it will occur m-1 times the previous row. And how do I prove that true? Well, I look at the definition again. U over u will occur an m-2 number of times. But then if we recall that second to last child, that u over u plus v from that fraction u over v, then that fraction will be able to produce more u over u's. And that'll also, since so that's saying out of every m children, there's only one child that can't. And that's that very last one, that u plus v over v. So that means m-1 children have the ability to replicate my original fraction. So that means m-1 times the previous row will hold as the number of copies that U over V will be able to replicate. And then the theorem is proven to be true. And this is probably my favorite theorem from this whole project, because I made a generalization. It's a cool, nice generalization about finding the number of times some fraction U over V will occur on any level of M trees. So I guess we're nearing towards the last bits of it. So I guess I want to make some comments on what I have researched. So this paper kind of did expand on the Calkin-Wilf tree. So we looked originally at what the Calkin-Wilf tree was, how it expands to the three-ary tree based on the Flowers and Lockhart paper. And given some of those observations, I was able to go in and I was able to code up the different levels of trees, the hyper m-ary sequences, and see what other observations I can make about the four-ary tree to go off and make some generalization about the m-ary tree. And it was nice to see that some of the theorems were hold. So if you recall the 3.1, which was, I believe, the core rate in Sellers, we know that was able to hold. And at least we're able to find the number of times that a fraction was able to occur. So this problem is very, I don't want to say linear, because once you get to the level 3, it's some of the stuff will hold, right? Because we saw that the nth, I remember when I was originally trying to go find the nth term in the sequence, I remember I was trying to find the four-ary trees nth fraction of the sequence, and Dr. Flower was like, oh, wait, that's already been done. And we look at the paper and go, oh, wait, that's already there. So while there is a lot to still be discovered, it was still hard to think of new things to what's to come up, but there are still ideas to still go through and find things. You just have to really think about it. But I do have some open questions and conjectures that I still was able to find, but I couldn't prove. So one thing that I was able to prove, so it's my second, well, not prove, but find, but was my second bullet point. So let's say I have some fraction A over B. If I have some fraction A over B, where A is equal to B, I want to find the number of times that that fraction will occur on some row R. So I have the recurrence in the next 2 slides, not on here. But I said, hey, if I have fraction 2 over 2, I can find the number of times that it'll occur. And it wasn't actually easy to see a pattern to formulate as a proof. You might think, oh, well, 2 over 2 should occur the same number of times as 3 over 3, but it actually doesn't. And what actually is cool, it finds out it occurs a double the number of times as 2 over 2. But again, I wasn't able to prove that. So I do have another conjecture on the next page. So this will work for any M level tree, but I list this as an example of, let's say, given the four-ary tree, since I kind of started with that in my paper. Given the four-ary tree, let's say we have some fraction A over B where A is equal to B, then I claim the following children will be as such: A over A, A over A, A over AB, and then B over A. So I wasn't able to go through and prove this, mostly because I ran out of time. So if you are in the audience and you're thinking about starting a thesis, try to start as early as you can, because the research does take a while. And eventually, once you get the literature review down, you go, hey, let me do new stuff, and then you run out of time. But I'm sure I probably could have been able to prove this to the similar logic that the three-ary trees, the Flowers and Lockhart paper proved that B would be the next numerator's fraction in the sequence, and that's already proven to be true. So I'm guessing we can use that similar style of logic of induction to prove the next denominator in the sequence when A is equal to B, that the previous fraction's numerator will be the next fraction's denominator. So I wasn't able to prove that, but assuming if I had more time, I would have been able to probably prove that. So the last thing I said was my comments on when fraction A was equal to B, the number of times it occurs. I was really hoping I could find a nice pattern for it, because once I first saw 2 over 2, so using Mathematica, I kind of not cheated a little bit, but found the closed form for it from the pattern. It told me it occurred 2 times 3 to the R minus 2 times 2R plus 1 times. And I was like, okay, this isn't really easy to see a pattern for, because the pattern was like 2, 10, I think it was like 42, and I wasn't able to easily formulate a proof from that. But then if I looked at 3 over 3, I was like, surely it must be the same, but it's not. It occurs actually double the amount of times 2 over 2 occurs. And I was like, well, wait, maybe 5 over 5 occurs the number of, or 4 over 4 occurs the number of time, double that, and then maybe it was double that. Unfortunately, I was not able to see that. I tried factoring out terms and looking at the sequences. It does not occur in that form. So no, I was not able to prove that. So hopefully if this question is left open, maybe somebody will be able to see, hey, I see a pattern for this, I can prove this. But these are left as open ideas. So I guess this leads to the end of my research, where I would like to thank Dr. Flowers for the idea, because I originally came to him with Ramsey numbers, I think. And he's like, wow, I don't know much about that, but here's this. And I read this idea and I was like, hey, this is kind of cool. So I do thank him for allowing me to extend some of his research and look at these ideas, and support for writing this, because I know at one point, I think he might have felt bad. He's like, I wrote a proof for when I did from the four-ary tree, And I proved that it occurred 3 times the previous row. And he's like, that's right. But he's like, we could do this in a better way. And I was like, that's okay. And I'm glad he did help me with that guiding process. And I do thank Dr. Atkins and Dr. Birch for sitting on my committee, because, you know, they could have just came in today and said, hey, good job. But they actually took time to, you know, he uploaded it to the Turnitin, and Dr. Birch wrote annotations and actually read my paper and gave me grammar. So I do appreciate that you guys spent the time to read my paper and give me good feedback. And I do thank Dr. Crispell for being able to motivate me to do a thesis, because I remember talking to him about this before. And I think I'm obligated to thank SCOME. So I threw in the SCOME scholarship, the SCOME code. So the last thing I want to say is my appendix. If you did want to see any code that I did use, I didn't include everything, obviously, because the Jupyter file was massively long, but I did include my 3-ary tree, 4-ary tree, and a bunch of the loops I used to find some of these patterns. Unfortunately, I did not include my hyper m-ary sequence partitions that it returns, because while it mostly works, I don't want it to be out there and then say, hey, you're missing a partition here, where if I got to, like, say hyper 555, it gives me 2 instead of 3, and I'm missing one. So I do intend, if I had free time or is able to continue this, I would like to actually make that code work for any integer n for any m. But that's the end of my paper, well, research. So these are all my 11 references. So I guess at this time, I will take questions, so I can leave it at that, or I'll just, I guess, maybe exit full screen so I can see if anybody commented in the Zoom chat.
Well, maybe we can first congratulate Jeffrey on his presentation and say thank you, and we'll send some virtual applause your way.
Thank you. I don't know where the Zoom bar is.
Okay, if anybody has any questions in the Zoom, feel free to, you can put it in chat if you want, and I'll read it out, or you can feel free to unmute yourself and ask. If there's questions in the room, Jeffrey, maybe just repeat them so the folks on Zoom can hear them.
Sure. I do have the audio on in this room, so they should be able to hear.
Can you make any conjectures about, so there's a difference in that those make a unique integer, you know, the integers are occurring once, right? So in the other trees you're looking at, they occur more than once.
Yes.
But are there any other connections to other problems that?
So using those sequences?
Yeah. Does it map to something physical?
Is it mapped to something? So Dr. Atkins asked if, so we use different hyper m-ary partitions to calculate these tree sequences, and he asked if they relate to anything else. So this was actually the first time that I learned about the hyper binary sequence, the hyper m-ary sequence, because I actually had to figure out what these were, and like, oh man, I remember like researching about this, but I did not find a whole lot of what else it's applied to. So that is something I would have to like look into, because I actually don't know any many other applications of what the hyper binary. So we know powers of 2, which was the, you know, the binary partition sequence. So I forget what slide that's on, but oh, right here. So that's used a lot more, because we can have powers of 2 being used for anything, right? So especially like computers are used for binary, maybe not necessarily powers of 2, but I don't know what other hyper m-ary applications there are at this time. I'm not sure. Sorry. Is there any other questions?
How long does it take your computer code to run when you were expanding?
So if I have my computer loaded up, I try. So Dr. Crispell, you are a magical man, because you can have your personal computer with these set up at the same time. I cannot. I tried signing in so I could have my computer loaded. It just kicks me out. I was going to have my code loaded up if anybody wanted to see it. So eventually it does take a while to run if I increase the tree size. So when I wanted to print these, so for depending on how I wanted to go, it started to burn up one time. It was spinning around. It was getting pretty loud. It does take a while to run. So I kept it pretty low. I think I kept it as like the 8th row, maybe the 7th row, because eventually once I got so far, I mean, these trees, especially when you get to the larger the M, it gets pretty large that I remember letting it run one time for like 10 minutes because I expanded to like the 20th row and it gets pretty high. So yeah, it can take a while depending on, so I could probably scroll down to the code. I mean, sorry, I think somebody just asked a question. I didn't mean to interrupt, but
As computational mathematician, 10 minutes is nothing.
10 minutes is nothing, right? But I was like, man, I could for research purposes, I can lower the levels, right? I can lower it.
If it hasn't run for a week, it's done. Do you pickle your output so you can look at it again later?
Like you mean save it?
Yeah, well, in Python, you can pickle it.
So I did not pickle it as certain, I guess, I remember you told me you could do that once, but I did not save it that. So it's in Jupyter. So whatever's in Jupyter, whatever's left as an output state, at least stays there, but I didn't pickle it. I know what you mean, like save it as for later so I can,
Yeah,
goes up like what, checkpoint?
well, no, you can take your output, your tree or whatever, and whatever its data structure is, and then just pickle that out. And then you could load that pickled object back in without having it change, and it would still be able.
So you can compute to row 8. and then
Oh,
you go
okay.
back and say, let's load row 8
And then continue
more rows.
That's smart. I should have done that. I didn't know how to do that at that time in Python. That is cool. So they made the observation of saying, store some code as a pickle in Python, right? So I could have saved my output and then generated later trees and got, I could have seen that. I didn't know how to do that at the time in Python. So I just, obviously started from scratch, click run and see all the trees.
Yeah, if your code's getting where it's running for a half an hour, you don't want to spend that time next time.
Right.
You can just put in it's a simple pickle reference.
Cool. Yeah, I'll have to look up documentation how to do that. Thank you. Yeah.
So I have one other, and I don't think this is really just could you do something in this regard? So you start your trees with 1 over 1 and you work from there. So can you, if you're given, if I gave you, I don't know, 13 over 7, could you compute how far from 1 over 1 I was?
Yes. So we can actually, so it's actually my code. I don't have the code loaded up. I wish I did, but yeah, so we can actually find the term in the sequence that it is. So if we know what fraction that it is or what number it is in the sequence, yeah, we can subtract it from the initial to see. We can count to see based on the partitions, the number that is in the sequence. I forget what it is off the top of my head. We actually coded it in Python. So I actually coded so tables of it. So you can actually see the nice aligned tables using the, what's it called, the dot format. So I actually was able to see some of that, but I don't remember exactly what it is off the top of my head. I'm trying to find that, but I was able to do that.
So you can compute it. Could you find a closed form for given a different A over B, figure out what?
Yeah, so I can change the root to be whatever I want. And yeah, I can, it would change the sequences slightly, yes.
So looking to say, so
Oh, sorry.
can you predict what row an A over B fraction appears on the first time it appears?
I believe so. Yeah, we probably can, because if we know the patterns of what it comes from. So that's actually what we're leading into next. I think Dr. Flowers gave me that idea. He said if we knew the multiples of the previous fractions, we could use that to predict the next one, but we didn't get to that, but we were thinking about it. So actually, yeah, good. I think that was exactly what Dr. Flowers suggested before.
I'm going to show a little ignorance here.
That's okay.
Well, it looks like there's definitely a fractal nature to this, right? The tree is within the tree,
Mhm.
and within the tree, and within the tree. So is there any way that is mathematics of fractals that are related here in any way?
I'm not sure, actually.
So do you want to like paint a color to ranges
Yeah.
of numbers and then see what the colors of the tree is?
This right, it seems like it's spiraling down, right? And there's tree within tree within tree, but they're all similar fragments, right? Like you cut that off, just start again. And it feels like it's going to paint itself the same way down that branch. You can kind of like trash part of the tree and it's still going to propagate that same tree.
Right.
So there's a fractal nature of it there. I'm just curious if you could exploit some
So
the relationship.
So I'll go, it's not further, it's just different. So if you imagine the numbering the pixels on a picture, right? So this is 1 through n, 1 through m, and now you've got a set of different fractions. If you colored them based on the frequency that that fraction covers for a particular number of rows in your tree, you could get a way to have, you know, sort of a traditional ordering of fractions, right? 5/4, and then run some number about your trees, and then color that pixel, right?
Yeah, you could visualize it.
Yeah, we probably
For
could.
potentially a larger tree and see a pattern
Right.
that you couldn't see by looking at the numbers.
And that's probably doable in Python because we can just, you know, depending on that element or at least the way it's coded, we can just give it a color.
Instead of being limited to looking at 7 or 8 rows, with the color scheme like this, you could look at potentially, you know, hundreds.
Right.
So,
I think I would have probably been able to do more of that if I had more computational power. So I know what you said, let it run a week, but I couldn't always let my computer run for a week at a time or so, because eventually I remember it was running at one point for almost at least 10 to 20 minutes. And I was like, I stopped it. I was like, we're lowering the number. So
it's only a processor.
that's true, but I'm very particular about my technology. I don't like to overrun or break them.
I played a video game for more than an hour.
So, yeah, but I didn't build it. I mean, I was even crazy about untwining all of this today. This cord, it was actually all tangled up today and it was eating me alive by OCD to fiddle the cord. But if I had more computational power, at least if I did do that and I saw it larger, I probably would have done something like that.
Some like cloud mathematica or something too. Or
That's
cloud
cool.
computing. That way you don't have to worry about whether or not you overheat the CPU.
Because I'm just running, yeah, streaming a computer.
Use somebody else.
Yeah, like today that actually crashed on me. It turned on, it said your fan is not working, do not use, and it turned off. And I was like, are you kidding me? And I got very nervous and scared this morning. I was like, I just need this today. And then I turned into the BIOS. I went to the fan, and it did a fan test and a thermal cooling test, and it was perfectly fine. I plugged in, speeded up, and it turned the fan on. So I was like, whatever. So, but that did give me some anxiety this morning. It's only a computer. Sorry, I didn't mean to deter away for a moment.
Okay, so we'll kind of do a last call for questions from the general audience, and then after that, we'll have folks leave so the committee can talk to Jeffrey a little bit. So anybody from the audience have any other questions before we wrap up?
Sorry. I'll mute myself.
Okay, so we'll thank Jeffrey one more time and give another round of virtual applause from those of us in Zoom. And we'll thank everybody for coming today, and ask Dr. Birch, Dr. Atkins to hang around, and we'll talk to Jeffrey a little bit here after everyone leaves.